Welcome to what I think is now the fifth part of this warm-up video for the second IGCSE paper in chemistry in 2018. So let's get going. Right, this question I've included because it is about dynamic equilibria. And you can see they've given you an equilibrium that you might not have seen before. And how can you tell from the equation that the reaction is reversible? Well, because it has that lovely reversible reaction symbol there. And now I'm slightly regretting colouring it in quite such an exuberant fashion, because I'll need to see that. So there's the symbol. Now, this is a question that my class in the last couple of years have often got wrong. You need to make 2 points about a dynamic equilibrium. And the first point that you must say is that the rate of the forward reaction equals the rate of the backwards reaction. They occur at the same speed, which means the amount of product and reactant does not change. The amount of the product and reactant are not equal necessarily. You might have far more product than reactant or vice versa, but because they are being formed and removed at the same speed, their amounts do not change. Now, when the pressure of an equilibrium is increased, the equilibrium moves to the side of fewer gaseous molecules. Now, in this reaction here, we've got 2 gaseous molecules on the left and only 1 on the right hand side. So if we increase the pressure, the equilibrium moves to the right, and therefore you increase the amount of N2O4. And what happens when temperature is increased? Well, when temperature is increased, the reaction moves to the endothermic direction. The reaction almost tries to absorb the energy that you yourself have added through increasing the temperature. So we need to look at this bit of information here. Now, this tells us that delta H is negative, and that means the forward reaction is negative. That means the forward reaction is exothermic, which means the backward reaction is endothermic. So when the temperature is increased, the reaction moves in the endothermic direction, so we decrease the amount of N2O4. Now, why is it important that oxides of nitrogen are not allowed to escape into the atmosphere? Well, oxides of nitrogen are acidic. They're acidic gases, and they react with water vapour to form acid rain. Now, how might you know that an oxide of nitrogen is acidic? Well, nitrogen is a non-metal, and non-metals form acidic oxides. So 2 problems that can occur with acid rain. Well, the first problem is that it could kill marine life in lakes and rivers and things like that by making the water in there too acidic. It could damage crops and plants by making the soil that the rain falls on too acidic. The acid rain itself could react with limestone. Now, that might in itself not seem a massive problem until you consider that a number of constructions are made from limestone. Statues are made from limestone, so they would react with this acid rain and they would corrode. So there are a number of problems you could come up with there as a result of acid rain. Now, the next question is an organic question, and I really like this question. In fact, I don't like it as a question because it traps people, and I understand why it traps people. But I've included it because I remember it trapping people. Quite often people here forget to talk about the word hydrocarbon. They don't explain that it's a compound containing carbon and hydrogen only, and they just focus on unsaturated, meaning something that contains double bonds. Now, another key definition: what are isomers? They are substances that have the same molecular formula but a different structural formula. Now, I told this story in an earlier video about a student of mine talking about how to remember what an isomer is, and that because it contains an M, that refers to the M here, and that just helped him remember this. Now, the next question asks us to draw some isomers of C5H10. Now, that should be very clear immediately that that's going to be some kind of alkene, because it fulfills the CnH2n general formula. So let's put 5 carbons in a straight line, and let's put our double bond there. And I'm just trying to make single bonds there. So this carbon on the right hand side needs 2 bonds because it's already formed 2 here. We've got a carbon here which needs 1 bond because it's already got 3, and then you've got 1 bond there, 1 bond there, 1, 1, 1, 2, 3. And I'm not going to bother writing the H's on the ends of the bonds just to save time. Now, what we could also do is move the double bond. Rather than it being at the end, we could have it on the second carbon. So let's have it here. And again, let's put some bonds on. So this carbon needs 1, 2, 3. The carbon next to that has already got 3 bonds, so it only needs 1 hydrogen. The carbon here also needs 1 hydrogen. This carbon in the middle needs 2, and this carbon at the end needs 1, 2, 3. And each time you should add your hydrogens on, obviously, up here. But you should also check the number of bonds you got. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we fulfilled C5H10. Now, we need to come up with a third, and I'm running out of space. And a remarkable turn of events. I've managed to use the computer program properly. So let's try adding a branch. So let's do 4 in a straight line. Let's put a double bond here, and let's put a branch here to put the carbon here. Again, put your hydrogens on. And you can see that I'm going to now count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, okay. Are there any others? Yeah, there are absolutely loads. I really wouldn't have fancied marking this question. We could have moved, we could have put this branch here on that carbon, which would have been fine. We could even have made a pentagon, a cyclic alkane, which some of you may have come across before. So we've got our 5 carbons in a ring, and each carbon will need to have 2 hydrogens off it. And this structure will be very, very different in terms of its reactions to these structures, because this structure contains no carbon-carbon double bonds. So this structure will not react with bromine water and lose the orange colour of the bromine water to form a colourless liquid, because it's got no carbon-carbon double bonds. And lo and behold, as soon as I start talking about alkenes reacting with bromine water, here is a question on that. So state the colour change C in this reaction. We will see something going from orange to colourless. And the displayed formula of the product of the reaction of bromine with ethene, well, this is an addition reaction. So if I just draw out ethene very quickly, in this addition reaction the double bond is going to break, and you're going to get the bromine atoms added either side of where the double bond once was. So this is your answer to the question. You can see the double bond here has broken, and because of that we've needed to add on an extra atom here, an extra atom there, and lo and behold, those are the bromines in this reaction. Now polyethene doesn't react with bromine like that because polyethene does not have a double bond. Okay, the double bond in polyethene was broken when it was formed, because ethene had the double bond and that was broken, so each ethene unit could bond to its neighbours to form that long polymer chain in polyethene. And that concludes this part, and I think there might just be one to go.